Welcome to 2.6. Today we're going to talk about cylinders and quadratic surfaces. On the last page there's a review of conic sections, and you might want to do that first because we're going to be talking about a lot of conic sections today. In math, cylinders don't have to look like your typical Coke can. These are all examples of cylinders here, and the way to identify a cylinder by its equation is there's a missing variable. You can see in each one of these equations here, there are only two variables present. I'm going to show you how to sketch a cylinder. You're going to start by sketching the generating curve, and you're going to sketch that in the plane of the variables you're given. So in this example, I'm in the YZ plane, and I'm going to sketch a hyperbola that looks like this. Again, you might want to go to that last page if you're not recognizing that. Okay, then you go to R3. I've got X here, Y, Z, and in the YZ plane, I've got that hyperbola, and what I do is I extend it along the axis of the missing variable. And so that's going to give me a shape that looks something like this. That's not the greatest picture. I'm going to show you that picture in Calc 3D right now. Okay, so here I am in Calc 3D, and I will need to select an implicit surface in order to graph this. And I type in my equation, and there's my cylinder. And I'll clean it up a little. That's a much better picture than the one I had. Now, we're going to use this example on the bottom of the page, so we're going to come back to this in a minute. Okay, let's do another one. X squared plus 4z squared is 16. Well, that's an ellipse, and it looks like this. And the x-intercept is 4, and the y-intercept is 2. And so I go to R3, and I sketch that ellipse in the xz plane, and then I extend it along the y-axis. So that's going to look like a big tube. Okay, sometimes we can find out things about surfaces without actually graphing the whole surface, and we look at the traces. So the trace is a curve formed by intersecting the surface with a plane. Typically, we choose the coordinate planes. For example, the xy trace is found by intersecting the surface with the plane z equals 0, because that defines the xy plane. So let's go back to our cylinder here, y squared minus z squared equal 1. We're going to find equations for each of the traces and describe them with a single word. So the xy trace, we want to set z equal to 0 in that equation. So I get y squared equals 1, which gives me two curves actually, y equal plus or minus 1. That's two parallel lines. Okay, and here I am in Calc 3D. I graphed the xy plane by setting z equal to 0, and you can see the two lines I'm getting here give me the xy trace. Okay, yz trace, we're going to set x equal to 0, and we get y squared minus z squared equals 1, and that's the original hyperbola. And I'll do that in Calc 3D. In order to set x equal to 0, I need an equation of the form x equals. So I have to select that from my list here. And there you can see the intersection of the plane with that cylinder is giving me the hyperbola that we just found. And finally, the xz trace, we're going to set y equal to 0. And we get negative z squared is 1, or z squared is negative 1. Well, that can't happen. So that's empty. And let's take a look at that. Here I've graphed y equals 0, which gives me the xz plane, and you can see it's not intersecting that surface anywhere. Okay, now let's talk about the quadratic surfaces. These are the 3D analogs of the conic sections in R2. And there are 6 quadratic surfaces. You don't have to memorize them, but it is helpful to be familiar with each of the equations. And I've color-coded them in terms of groups. So the first 3, ellipsoid, hyperboloid of 1 sheet, and hyperboloid of 2 sheet. Notice in the standard equation, they're each set equal to 1. So that's something they have in common. And what distinguishes between the 3 is the number of minus signs between the quadratic terms. So an ellipsoid has no minus signs, a hyperboloid of 1 sheet has a single minus sign, and a hyperboloid of 2 sheets has 2 minus signs. Okay, an elliptical cone is in its own category. It's got all 3 quadratic variables, but it's set equal to 0 over here, and there's a single minus. And finally, we've got the 2 paraboloids. We've got an elliptical paraboloid and a hyperbolic paraboloid. And the way you can tell you have a paraboloid is there's a linear variable. Notice here it's z equal, and what distinguishes between the two is if there's a minus sign or not. For an elliptical paraboloid, there's no minus. And for a hyperbolic paraboloid, there's a single minus, and typically we call that a saddle surface. All right, let's do some examples. We want to classify each surface and then describe the traces. So for the first guy, I'm going to divide both sides by 12 to get this into standard form. So I get y squared over 4 minus x squared over 3 minus z squared equals 1. That's a hyperboloid of 2 sheets. And since the y squared is the positive variable, this is going to open along the y-axis. So it'll look something like this. It's a hyperboloid of 2 sheets, but it's oriented along the y-axis, not the z-axis. Okay, xy trace, set z equal to 0, and I'm going to set z equal to 0 in the standard equation here. So y squared over 4 minus x squared over 3 equals 1. That's a hyperbola. So I want you to both be able to find the equation for the trace and to recognize it. That's very important. Okay, xz trace, we're going to set y equal to 0, and we get negative x squared over 3 minus z squared equals 1. Well, if I multiply both sides by -1, I can see that that's going to be the empty set because the left side is non-negative and the right side is negative. So this is empty. And you can see that up in my picture here. If I were to intersect this surface with the xz plane, that plane would go right in through the middle and it wouldn't intersect the surface anywhere. Okay, next one we're going to look at on Calc 3D. First, let's do it by hand. We're going to write this as x equal y squared plus 4z squared. So we know we've got a paraboloid because there's a linear variable, and in this case we have an elliptical paraboloid. And it's going to open on the x-axis. It's going to look like that. Okay, xy trace, we're going to set, I won't write that anymore, we're going to set z equal to 0, and so we get x equal y squared, and that's a parabola. And the yz trace, we set x equal to 0, and we get 0 equals y squared plus 4z squared, and that's a single point. So let's take a look at this on Calc 3D. All right, I've already graphed our paraboloid, and now let's look at those two traces. The first trace was the xy trace, so I want to intersect with the plane z equals 0, and that looks like that. And we can see that we're getting that parabola right there on the intersection, and then I'll clear that out, and then we want to intersect with x equals 0, so I need another equation of the form x equal, and we can see there we're just getting the single point, which is the vertex of that elliptical paraboloid. So I encourage you to explore all of these on Calc 3D. It's super helpful and it's kind of fun. Okay, next one, this is a cone, and let me write it as z squared equal x squared plus 4y squared. It's an elliptical cone and it's oriented on the z-axis. So it looks like your typical cone. XY trace, we can see that that's going to be a single point, but let's verify. We're going to set z equal to 0, and we get x squared plus 4y squared is 0, and indeed that's a point. And then YZ trace, we're going to set x equal to 0, so we get z squared equals 4y squared. Well, that's two curves. That's z equal plus or minus 2y. And so that's two intersecting lines. And you can kind of see that if you look at my picture, but you might want to explore that further on Calc 3D. Okay, this is a pretty short section, and that is the end.